Hello everybody and welcome back to another video on my channel. Now, there has been a lot of videos in the past on this channel about forces, and today I'm going to make an attempt to reconcile all of them. This video will essentially cover pretty much everything you need to know about forces in order to be pretty good at them. So, without further ado, let's move on to the video. As I said earlier in the intro, today's video is about Newton's law of motion. Specifically, he has three of them: the first law, the second law, and the third law. Now, each of these laws represent different concepts of nature and fundamental rules in physics. But we will not really be covering them first, second, third. We'll be covering them. I'll start with the first law, then I'll go to the third law, and then for my final thing, I will be covering the second law of motion, arguably the most famous equation in all of physics. So, now that we have both of the things done, what laws there are, and how the order we're going to cover them, let's move on to actually discussing about these laws. For our Newton's first law, what we're going to have to do is first talk a little bit about a concept called inertia. Now, inertia is simply, at least for now, we can define it as an object's resistance to motion. Now, the reason we needed to know this is because Newton's first law is literally called the law of inertia. And it states that an object has inertia. So, what happens over here is an object has inertia, or a resistance to motion, has inertia, and it'll resist an outside force. An object has inertia, or an object will continue in the path of its motion. Now, in the path of its motion, it doesn't always have to be moving. It can also be stationary. And then, unless an external force is applied on it. So, that is essentially Newton's first law in a nutshell. Now, the thing is, these both, an object has inertia, and an object will continue in the path of its motion unless an external force is applied on it. So, now that that's corrected, what we're saying, now both of these are both a completely valid ways to write Newton's first law. First, an object has inertia, and an object will continue to be in the path of its motion unless an external force is applied on it. And remember that the path of its motion also means that it could be stationary. So, that's essentially Newton's first law. Now, let's move on to the third law. The third law states that every object has an equal and opposite reaction. So, let's write that down. Now, what could I possibly mean by equal and opposite? If it's equal, how can it be opposite? How can they both be true at the same time? Well, what we're trying to say here is not necessarily that it's going to be equal and opposite in both, but it's going to be equal in magnitude, but opposite in direction. And this was actually covered earlier when we were talking about in our math review for mechanics, when I was talking about vectors, and in my forces video, as a force is a vector, so it has a magnitude and a direction. So that's how we know that every action has an equal and opposite reaction, where action, of course, means force. Another way to write this law is to say F of 1 on 2, or the force of object 1 on object 2, is equal to the force of object 2 on object 1, And then you'll normally draw it with these two bars around it to show that it's the magnitude of the vector. So now that we know the first two laws, let's move on to the third and arguably most important law, which is the second law, because it's the third law we're covering, that's why I said third law, but it literally is the most important equation in all of mathematics. And it can simply be written as F is equal to MA. That simple. But it's so profound in the fact that how many places it can be used and how almost universally true it actually is. Now, by the F, I mean the net force, F net, or when you do this, or F net, either one works. And in the second law, this also states the fact that force and acceleration are proportional. And this is huge because since force and acceleration are proportional, and you can get acceleration and you can get velocity and distance from acceleration, this forms a clear link between kinematics and dynamics, which are some of the sub-branches of mechanics. So everything starts to come together. An inclined plane is pretty simple when you look at it. It's basically, you have one line here, and one line here, and that makes a triangle. Now this triangle has an angle of theta degrees with the horizontal. So what does this actually do? Well, its real magic comes when we put a block on it. So there's a block over there. Let's say this block has a mass of m. Now its weight, which is gravity, is downwards, which is mass times gravitational acceleration. But as you can see, this plane is on an incline. So the question is, how can we predict motion when our plane is not in the same direction as gravity? The answer to that lies in splitting gravity up into two components. One component, which is perpendicular to the plane and is going inwards, so like this. This is mass times gravitational acceleration, so the weight of the object, times cosine of theta. And one direction parallel to the plane, which is mg sine theta. So that is the answer to our question and the basis for all things involving inclined planes. Basically, we're splitting up gravity and all other forces in either the horizontal or vertical direction into a component perpendicular to the plane and a component parallel to the plane. So I think that's really about it for our explanation, and we will get more and more knowledge when we come to use these concepts in problems in accordance with Newton's laws and kinematics. So let's get started on our first problem. Over here, we have our first problem. Now, if we just look at it head on, this is a lot of words and it might seem incredibly confusing. But let's break this down step by step. So first of all, there's an inclined plane with an angle of 30 degrees with the horizontal. The mass of an object on this inclined plane is 3 kilograms. So that's that. Friction is non-existent in the scenario, and assume g is equal to 10 meters per second squared. This will be constant for all of our problems, so I will not be writing those two sentences for the next 3 or 4 problems. And what next is find the force required to balance the object where the direction of this force is parallel to the incline. Now, right now, feel free to pause the video if you know this and solve the problem so you'll get your practice in and you'll also get better at the concept and possibly develop a greater interest for it. But if you don't know how to solve it, which I'm assuming is a decent chunk of you, stay along and let's walk through it together. So over here, I have a few things highlighted. So first, we have an inclined plane. So we already know we're going to be talking about what I talked about earlier in the video. So let's have this inclined plane of angle theta, which is equal to 30 degrees. Now the mass of an object on this inclined plane is 3 kilograms. And friction is non-existent. Assume g is equal to 10 meters per second squared. And the last part is find the force required to balance the object where the direction of that force is parallel to the incline. So, as we saw earlier, the force mg sine theta is the force that is trying to put this towards the ground and is making it slide down the plane. Now we want a force that is equal in magnitude and opposite in direction to this mg sine theta, so it neither moves up or down. So that means the net force is equal to 0. Okay, so now that we have that done, F net is equal to 0, that's one thing. And now that we know exactly what our force is, let's start plugging in the values and figuring it out. So if the net force is equal to 0, then our force minus mg sine of theta is equal to 0. So our force is equal to mg sine theta. Now let's plug in our values. Our force is equal to 3 times 10 times sine of 30 degrees, which is equal to 30 times 1 by 2, which becomes, after simplifying, 50 newtons. And this is the answer to our problem. So this just shows a very basic application of this inclined plane, and it shows very simple how one can do what they do. So that's pretty much about it for this problem, and let's move on to our second problem. Over here, we have our second problem. This problem states there is a block with a mass of 1 kilogram on an inclined plane with an angle of 30 degrees. The length, hypotenuse of this inclined plane is 10 meters, and the object starts from the top of this inclined plane, and this object also starts at rest. Find out the time it takes to get to the bottom of the plane. Now, if you know this problem or you want to try solve it on your own, feel free to pause the video, just like I said in my last problem, and work it out on your own. But if you want to see me walk through this problem with you, feel free to continue watching. So, for those who have stuck around and are continuing to watch me, here we go. Problem. This says that there is a block with a mass of 1 kilogram, and then our incline is 30 degrees. The length is 10 meters, and we start from the top of this inclined plane and at rest. And what are we trying to find? We are trying to find the time. So, what we can do is first, let's draw our inclined plane. This is 10 meters. 10 meters. This angle is 30 degrees. Then after that, our block over here is starting at the top. This block has a mass of 1 kilogram. Now, of course, I said it's frictionless and gravity is 10 meters per second squared in my last question, and I said it's assumed for the rest of the questions. So there goes that, and this is really all we need to solve the problem. So let's go. So there are multiple equations from the Big Five or kinematics that we can use to find time, as the only way we know how to find time as of now is through kinematics. So we have two problems. We have the distance is equal to v0 plus 1/2 of a times time squared, or we have vf is equal to v0 plus the acceleration times the time. Now there's also velocity is equal to distance times time, but these are very important right now for reasons that I'm going to show you in a bit. So that formula is automatically crossed out. And also, the reason I crossed out that formula is because it has velocity, or really final velocity, and final velocity is very annoying to deal with. So let's also cross this out. So the only formula left, and it turns out the best formula, is x is equal to v0 plus 1/2 of at squared. So this is our formula that we are going to use. So if we plug in the numbers, then what we already have, so our distance is 10, so we have 10 is equal to 0 plus 1/2 times our acceleration times time squared. Now, let's find out this acceleration. Now, our acceleration is the acceleration that is parallel to this incline down the ramp. Now, we know from earlier that our force is equal to mg sine theta, but our acceleration is equal to force divided by mass because of Newton's second law, which I already said earlier that we are going to be using Newton's laws and other stuff in this. So if you just realized, make sure you go back to those videos on my channel and make sure you watch those. But now that we know that F is equal to ma, we know that mg sine of theta is equal to mass times our acceleration, and our acceleration, when we divide by m, is equal to g sine theta. So now that we know our acceleration, let's evaluate. So we have 10 is equal to 1/2 times g, which is 10, times sine of 30 degrees times time squared. So 10 and 10 cancel out. Sine of 30 is 1/2. So 1/2 times 1/2 is equal to 1/4. And multiplying by 4 on both sides gives us t squared is equal to 4. And as a result, the time is equal to 2 seconds. So the time it takes to travel to the bottom of this plane is equal to 2 seconds. Our third problem looks very similar to the first problem, but has one key difference. This problem reads an object of mass 7 kilograms is on an inclined plane with an angle of 60 degrees. Find the force required to balance the object and keep it from falling. The direction of this force is purely horizontal. Now this creates entirely new implications on how we have to solve this and adds one extra step that most people might not realize. So, as of always, if you know how to solve this and you want to practice, please feel free to pause the video and practice this problem. But otherwise, I would highly recommend watching through with me, as this is slightly different and you might not understand it at first. So, let's first get our basic setup. We have an inclined plane of an angle of 60 degrees. And now we have some mass with an object mass of 7 kilograms. But instead of having our force be parallel to this inclined plane, we have it be purely horizontal. So if this is our force, this would be our mg sine theta, and our perpendicular would be our mg cosine theta. Now, let's look at this force F first. So now this force F is purely in the horizontal direction, but if I draw a line over here, and this angle is 60 degrees, and then I draw a vertical line, so this is a 30, 60, 90 right triangle, this side becomes F divided by cosine theta, because this side, the hypotenuse, times the cosine of the angle, which is 60, is equal to the horizontal, which is F. So now we know this is F divided by cosine theta. And since that's in the same direction as our mg sine theta, since our net forces has to be equal to 0, we're going to have F divided by cosine theta is equal to mg sine of theta. Then what we have is F is equal to mg sine theta times cosine theta. Now, we have our angle 60 degrees and our mass and our given gravitational acceleration. So, we can plug in the values and solve for F. So, F is equal to 7 times 10 times sine of 60 degrees is the square root of 3 by 2 times the cosine of 60 degrees is equal to 1 by 2. So now that we have that, what we can do is we have 7 times 10 times square root of 3 by 2 times 1 by 2 is 70 times the square root of 3 by 2 times 1 by 2. Now this becomes, if I drag this all the way over here, this becomes, if I have 70 and 2, 35 root 3, and then 35 root 3 divided by 2. So F is equal to 35 times the square root of 3 divided by 2 newtons. Because what happens is, since we have F divided by cosine theta is equal to the hypotenuse, because cosine theta is always less than 1 or equal to 1, and the hypotenuse is always greater than the edge length. So it makes sense why it would be F divided by cosine theta, as it's an adjacent. So what we have, and this is equal to mg sine theta, and plugging it all in gives us a force of 35 root 3 divided by 2 newtons, and this is our answer. Basically, this problem revolved around realizing that the force that would balance it in the same direction has magnitude F of cosine theta, but our actual force would change depending on the angle that it is given at. So that's our third problem, and let's move on to our fourth and final problem. This is our fourth and final problem for today. This problem states an object is on some inclined plane with an angle of theta. This, for the force of gravity perpendicular to the plane, is 100 times the square root of 2 newtons. The force of gravity parallel to the plane is also 100 times the square root of 2 newtons. Find theta and the mass of the object. So, what we have over here is, if the force of gravity perpendicular to this plane is 100 times the square root of 2 newtons, that means mg times cosine theta is equal to 100 times the square root of 2. Now, the force parallel to the plane is mg sine theta. So if this is also equal to 100 times the square root of 2 newtons, what is our angle theta and our mass? So one thing you can do is, when you're given forces parallel perpendicular, or you have pretty nice equations with sine theta and cosine theta, and you to find theta, is you should have the equation with sine theta, divide that by the equation with cosine theta. So mg sine theta divided by mg cosine theta is equal to 100 times the square root of 2 divided by 100 times the square root of 2. Now mg gets cancelled out, 100 square root of 2 cancels out, and sine theta divided by cosine theta is equal to tangent of theta. So tangent of theta is equal to 1. That means theta is equal to the tangent inverse of 1. And by knowing our identities, we know that theta is equal to 45 degrees. So now we have one of our two answers. Our next answer revolves around finding the mass. Now, let's plug theta is equal to 45 degrees in any one of these equations. Let's do mg sine theta. So if mg sine theta is equal to 100 times the square root of 2, that means m times 10, which is g, times the square root of 2 divided by 2, which is sine of 45, is equal to 100 times the square root of 2. Now, square root of 2 times square root of 2 cancels out. Dividing by 10 on both sides gets us 10, and then multiplying by 2 gets us 20. So our mass is equal to 20 kilograms, and that is the answer, the second answer to this problem. the first thing that we're going to be talking about is a force called tension. Now, normally, what will happen is you're going to have some sort of thing, like let's say this block, and then we have a string over here. Now this string over here connects the two blocks, and if I apply a force on one of those blocks, that force will get transferred to the string in the form of tension, and this tension will pull this other block with another acceleration. So that's essentially the basis of tension and the basis of pulleys. Now, the reason I'm not doing a whole video just based on tension is when I do a video on pulleys already cover tension, and there's a lot more problems online and just in general that you'll find on exams and other stuff about pulleys versus just pulling a block with a string attached to it. So that's basically the reason I'm choosing to do a video about pulleys. But now, let's get actually into what a pulley is. So, when I have a pulley, I'll draw a pulley like this. This is the thing that rotates the object, and I'll have two pieces of string on the side. Now, this string wraps around this all the way, and oftentimes we'll have it connected to these two blocks or some other objects. So basically, what's over here is, let's say this block is M1 and this is M2. What's going to happen is, since the string connects all the way, this will have a tension of T. Or another way, which is the better way, is tension is constant between two masses. So now, since we're assuming that this pulley is light, which is something I probably should have said earlier, but we assume all our strings and our pulley is going to be light for this video, and maybe in the future I'll have a more advanced video showing what happens when the pulley is not light. So the tension is constant between two masses, and it changes when we don't. It changes after another mass. So if we had this and another string connected to a mass of M3, this would have a different tension, and this would also have a different tension. So that's essentially how this works, and how about 90% of our pulley problems are going to be solved. So I think that's about it for our explanation. That's pretty much all the new stuff you need to know about pulleys, and let's move on to solving some problems. Alright, so this is our first problem, where we have our light pulley, just something that connects it up to the ceiling, and two masses hanging from a piece of string. So what we know is the mass of our first mass is 3 kilograms, the masses of our second mass is 5 kilograms, and we assume that gravitational acceleration is 10 meters per second square. So first, find the acceleration of both blocks, and B, find the tension in the string. Now, for those of you that already know this video and that already know this type of concept, and you're using these videos to practice and work on that, make sure to pause the video and solve it on your own. And even if you're just learning this for the first time, it is a good idea to pause and try and solve it on your own. But for those of you who are still here and have not paused the video, let me walk through this problem with you. So the first thing is, let's look at mass of 1. Let's draw a free body diagram. So we have, this is our M1. Now the tension, since M2 is heavier, the tension is going to be pulling M1 upwards, because this M2 is downwards, so the tension is upwards over here. So the tension would also be upwards over here. So that's basically how that works. So this is our force T, and downwards is m1g, or the weight of the object. So now we know that the net force is equal to mass times acceleration. So m1 times our acceleration is equal to our tension minus m1. So m1 times our gravitational acceleration, as this is our net force. Now if we draw the same thing for number 2, where instead of m1g, this will be m2g, that means that m2 times the acceleration. Now since m2 is greater than m1, it's a little out of common sense, but we'll know that m2 is the mass that's headed downwards. So our acceleration is m2g minus our tension. Now, we don't know what tension is. So what we can do is we can add these two equations together to cancel out tension. So we get m1 plus m2 times acceleration is equal to what we have is m2 minus m1 times times gravity. So when we plug in all the values and we do this over here, our acceleration is equal to m1 plus m2. M2 minus m1, so 5 minus 3 over m1 plus m2, 5 plus 3 times gravitational acceleration, which is A is equal to g by 4, which is equal to 2.5 meters per second squared. And that is our answer to our first part of this question. Now, what we wanted to figure out is what our tension was. So let's use one of these equations. Let's use the first one. So m1 times the acceleration, so 2.5 times our mass, which is 3, is equal to tension minus m1, which is again 2.5, 3 times gravitational acceleration, which is 10. This is going to be tension is equal to 7.5 plus 30, or our tension is going to be 37.5 newtons. And if we plug this into our other equation, that will also work for our answer. So that's our first problem done, and let's move on to our second problem. This is our second problem, and this problem involves a little less number plugging and more of understanding how algebra is involved within this problem. But first, let's say what this problem even is. So first of all, we have a pulley attached to the ceiling with m2 and m1 as different masses, where m1 is the mass on the left and m2 is the mass on the right. Now the thing with m1 is it's on an inclined plane with an angle of theta towards the ground. And this system is given to be in equilibrium. But what we want to do is we want to find the angle theta that allows this to happen. And let me add one thing in terms of m1 and m2. Now this problem is a little more basic form of some other problems that you might see on higher level exams, like the F is equal to MA exam, or something you might experience on an AP Physics final. So let's see how we can solve this problem. And as always, if you already know this concept and are using this channel for problems to study, or you're just trying to try this problem and see what you can do, go ahead and try and solve this problem. Feel free to pause the video and look at the end of this problem, where I'll always have timestamps to make sure that if you're right on this problem. So, let's get started on this problem for those of you who have not paused and are starting to solve this. So, now we know that this system is in equilibrium. That means the acceleration on both masses is equal to 0. So, acceleration, the net acceleration is equal to 0. That means the net force, F net, is equal to 0. So that's going to be very useful, as let's get started on writing our first equation in terms of this net force. Now, since our net force is equal to 0, that means we have a tension, T2, pulling towards upwards, or just T pulling towards upwards, and the weight of M2 pulling downwards. So 0 is equal to T minus M2 times the gravitational acceleration, G. Now, what also is 0 is the acceleration on M1. Now, if you looked at my last video for inclined planes, or if you already know this, you'll know that the acceleration downwards is g sine theta. So our force is m1g sine theta minus the same tension in the string. So, solving both of these equations for tension, we get tension is equal to m2g, and tension is equal to m1g sine theta. So, since both of these equations have tension over here, let's set them equal to each other. So, m2g is equal to m1g sine theta, and if we divide both sides by g and isolate sine theta, we get sine theta is equal to m2g divided by m1g. So, now that we have that, we can simplify and get sine theta is equal to m2 by m1, and taking the sine inverse of both sides, we get theta is equal to the sine inverse of m2 divided by m1, and that is the solution to this problem. So, that's really about it. Pretty basic algebra involved. Just the biggest thing is understanding that tension and the weight are the only really two big forces, and if those are equal, set the other forces equal to each other as tension is constant, and just do some very, very basic algebra to solve for theta. Today, we will be talking about friction and its more practical applications. So instead of deriving formulas or talking about friction very conceptually, I will give an overview of what you need to do, and we will solve some problems with it. This is like basically the way of friction that you will need to know if you need to solve problems or succeed in that way. And when you're doing derivations and other stuff, it is more useful in other fields and other concepts. But for now, let's get a quick overview of friction so we can move on to our problems. So, to begin, what is friction? Well, let's say we draw a floor and an object. If this object is moving on the floor, friction is going to be a force that opposes this. Now, this friction is dependent on many things. One, being the normal force, which is perpendicular to the surface, and I talked about a few videos ago. And if you haven't seen the rest of my mechanics series, be sure to go watch that. And the other thing that you will need to know is that this friction is also dependent on something called mu, or the coefficient of friction. This coefficient is only dependent on the surfaces and materials of the floor and the object, not on anything else. So, that's pretty much about it for what we're going to use friction today. Now, just a quick preview of what's going to happen in the next video. You will learn about contact force, where if I am moving an object this way, this is going to be my contact force, where I have a vertical and horizontal component, and I even have an angle with this vertical normal force that we will talk about in more detail in the next part of the video. But for now, let's talk about something different and something a little more practical, which is static friction and kinetic. So static friction, let's start with that. So static friction is the object is not moving. So basically what we're trying to do is we're saying, okay, I'm putting a force on this object in this direction, but static friction is opposing that force, and the force is in equilibrium, so there is no movement. Now, the thing with static friction is it is a variable force. So what do I mean by this? I mean that this can take on as many values as it wants up to a certain maximum. Now, what is this maximum? Well, the friction, which is written with this sort of lowercase f, over here I'll draw it in green, and then friction of static, maximum is equal to the coefficient of static friction, which is again dependent on the surface, and multiplied by the normal force. Now the derivation for this formula will be in the next video, which is going to be friction part 2. Now the friction, just the static friction in general, doesn't have to be that. It can be less than or equal to the coefficient of static friction times the normal force. So that's static friction. Now, what about the other type of friction, which is kinetic friction? So, kinetic friction is a little different in the way that the object is moving in this scenario. It has overcome the force of static friction. But the fourth thing with kinetic friction is it's a constant force. It's not dependent. It doesn't have any variable change. It can't take on multiple values. If you know the coefficient of kinetic friction and if you know all the variables involved, you can predict it completely with accuracy. But with the static friction, it could take on multiple values depending on how much force we put onto it. But the thing with kinetic friction is it's less than static friction. Because, let's say, we just overcame the force of static friction. And if kinetic friction was more than static friction, that means that we would have to overcome another force to get it to move. Again, because we haven't overcome that force. But that's what static friction is. So it leads to a contradiction, and that's not allowed. But what is kinetic friction? Well, kinetic friction is basically equal to the coefficient of kinetic friction multiplied by the normal force. Now, if you were paying attention, you would have noticed that there's different coefficients, which is the coefficient of static friction and the coefficient of kinetic friction. Well, again, these are constants that entirely depend on the surfaces, and they are not the same. Okay, this also, since it's less than static friction and the coefficient of kinetic friction is less than the coefficient of static friction by very simple algebra, that makes sense why if we start to get an object moving, a heavy object moving, it often feels easier to get it moving than, make it continue moving, than actually having it not move. So that's basically about it for kinetic and static friction and its relation to normal force, which was covered in my inclined planes video and my forces video about what normal force is. So that's about it for our overview of the practical applications of kinetic and static friction, or just friction in general. So let's move on to 2 examples that demonstrate it. Over here, we have our first example. Example 1. There is an object on the floor. It weighs 10 kilograms and a force of 20 newtons is being applied to it. The coefficient of static friction between the floor and the block is 0.3. Find the static friction force. So first, let's draw a quick diagram of all the forces. So we have the weight of the object, or mg. Then we have upwards, we have the normal force. Then we have our applied force, F, and then our frictional force, or static frictional force, towards the left. Now, since this object is not floating or sinking into the ground, the normal force is equal to the weight. And if we're assuming g is equal to 10 meters per second squared, where either way it doesn't make a difference to this problem, but we're going to, for this problem, assume g is equal to 10 meters per second squared, then the normal force will be 10 times 10, or 100. Now, if you remember, the static friction is equal to the coefficient of static friction times the normal force. So this is 0.3 times 10, which is equal to 30 newtons. But then why did I give you the force of 20 newtons? It's because I kind of lied to you in this. If you remember from earlier, this is only the maximum static friction that's equal to this. But if we want to find the actual static friction, as I said earlier, it's a variable force. And since 20 newtons is less than 30 newtons, the static friction will adapt. There will be no movement, so the force of static friction will be 20 newtons. And that is the answer to our problem. Now, in this problem, the reason I chose to do this problem is it's not just plugging in algebra, it's realizing that this is a variable force and this is not a constant force, and that's what separates it from kinetic friction. So that's that, and let's move on to our next example. Over here, we have our second example. Example 2. A block is on an inclined plane with an angle of 45 degrees. The block is moving down the plane with an acceleration of the square root of 2 meters per second squared. Find the coefficient of kinetic friction. So, over here, what we have is we have first an inclined plane. So, let's draw that. Over here we have this, and this. I know that's not really 45 degrees, but let's roll with it. So over here, 45 degrees, we have a block over here. So first, let's model all of the forces. Now, since mg cosine theta is this way, the normal force will be equal to mg cosine of theta, since it's perpendicular to the surface. Now, there are two forces acting in the direction parallel to the plane. We have, first, mg sine theta, which is what's making this to go downwards, and the force of kinetic friction. So, what we want to find is we want to find the coefficient of the kinetic friction. So, let's take all the net forces. First, we figured out that the normal force is mg cosine theta by taking net forces. And since we know that this block is moving down the plane, then we can say that the net force, or our mass, times our acceleration, which is going to be the one given in the problem over here, this is going to be equal to, first, mg sine theta minus the micro k, or our coefficient of kinetic friction, times mg cosine theta. So, now again, we'll assume g to be 10 meters per second squared for the purposes of this problem. So, what we're going to do is we are going to isolate everything. First, we can factor out m and divide it out of the equation, so that's not necessary. Then, what we can do is we can plug in our angle value of sine and cosine, and I think that's going to help us a lot. So g times the square root of 2 by 2 minus micro k times g times the square root of 2 by 2, since sine and cosine of 45 are the same. Now, factoring out g squared root of 2 by 2, we get a is equal to g squared root of 2 by 2, 1 minus micro k. So, now we know what our full equation is. Now, let's plug in our values for a and g and isolate the 1 minus micro k. So, we have 1 minus micro k is equal to, now this acceleration times the square root of 2 over g. Now, since g is equal to 10, and acceleration is equal to the square root of 2, so the square root of 2 times 2 is 2, so we get 1 minus micro k is equal to 2 over 10. Now, if we bring micro k and isolate it, we get micro k is equal to 8 over 10, or the coefficient of kinetic friction is equal to 0.8. So, that is our final answer and the solution to this problem. Now, as I said, this video is about theoretical aspects of friction. But the first place and the best place to start when discussing these applications or concepts is, what even is friction? Now, there are two main definitions of frictions. One that would probably be more of a mechanics definition, and one that would be thought of more of a chemical physics question or definition, or some sort of more advanced or molecular definition of friction. Now, I'm going to start with molecular definition, as I'd rather introduce you the mechanics definition a little later, so it stays fresher in your brain when we discuss more aspects about that mechanical definition of friction. So, let me introduce you to the molecular definition of friction. So, what happens is, let's draw a floor and a box. Now, this box, we'll have it moving along this floor. Okay? And now, let's zoom in to the molecular level. So over here, there's a bunch of particles or molecules in the floor, etc., etc. But when we have the box, this box is also made up of molecules. Let's do these a different color. So, now that when this box particles move, they start brushing up against these particles. So, tiny interaction happens, which is signified by these tiny arrows that I'm drawing over here. Now, these interactions cause a lot of energy and heat, energy, etc. But they also cause some force against the direction of motion, especially since when the particles collide, they lose some of their energy when they're not moving. So, since these particles collide and they release energy, and they lose a little bit of energy also. Because when we collide with other particles, conservation of momentum, which is a different topic we will discuss, or just generally conserving energy, which is a fundamental law of this universe, says that energy can't be created or destroyed, and it can be only transferred. And the transfer is the kinetic energy from these molecules into the molecules in the floor. So in fact, that's why the floor molecules will start bouncing around themselves also a little more, and they will heat up just a little bit. Now, if this doesn't make as much sense to you, you'll probably make it more clear when I start explaining conservation of energy in more detail. But I think that's about all you need to know for the molecular definition of friction. But I said there was a second definition, and one that at least I think is a little more useful, which is the mechanical definition of friction. Now, again, like the chemical definition, let's draw a floor and a box. And this box is moving this way. Now, what happens is we have our force of weight going downwards, right? mg. But then, to make sure this isn't sinking into the ground or floating, we have a normal force. Now, this normal force is the vertical component of something we call contact force, which is the force made when there's motion or when there's two objects in contact with one another. Now, where does friction come into all of this, you might ask? Now, if you watched my last video, you might remember that our friction formula, force of friction, is the coefficient of friction times the normal force. Now, as we'll see later, this coefficient of friction will have a different meaning down the line, but you should know that since this is related to the normal force, and this sort of forms a right angle like over here, and we have the normal force and we know friction is horizontal, friction is actually the horizontal force of this contact force, and we'll call the contact force C. But friction is the horizontal component of this contact force. So that's actually the real definition of friction in terms of mechanics. Now, this contact force is actually also comes from this molecular definition, as the molecules are also moving up and down, but connecting them requires some more advanced physics that has not been covered and that I'm not completely sure of myself. So that's essentially how the mechanical and chemical or molecular definitions of friction work. So now we know that this is how it works, but how does the contact force work? Like, what else can we withdraw or what else can we realize from this contact force? Well, number one, let's draw a new diagram so I can explain this. And number two, look at the contact force over here and the normal force and our frictional force. We are going to assign an angle. This angle is theta. Now, you could of course assign the angle over here. This could be theta or theta 1 or theta 2, but it will basically work very similar. And oftentimes in physics, we'll also be measuring angles from the vertical, just like we did in inclined planes. And many people find this to be a little more consistent and easier, as our derivation will involve using sine, cosine, and tan instead of sine, cosine, cosecant, secant, and cotangent. And those are slightly more complicated trig functions, and even though I'm pretty sure I expect you to know trig and they're still simple, it becomes harder to work with when we get into harder applications. So that's why we choose to have our angle from the vertical. So this vertical angle becomes that, theta, but our friction is micro n. So micro n and n, if we draw a right triangle over here with theta, n, and the coefficient of friction times n, with our contact force as a hypotenuse, by the Pythagorean theorem, we get the contact force is equal to n times the square root of coefficient of friction squared plus 1. So this is very, very, very useful, in fact. Now, while it might not be useful in more elementary physics, like something like honors physics or like early AP Physics 1, this will be much, much more important when we go into something like competition physics, like the F is equal to MA, or even the USA Physics Olympiad. So, since this is very important, what else can we learn from this? Well, we can learn that, of course, this depends on two forces, but in application of this, where I think you would be more clarity, is if we have a ramp, a force, and a tension pulling it in this direction. Now, this force, by Newton's third law, must have an equal and opposite force. So, we have this over here, our contact force, C. Now, by all other standards, you might think, wait, if it's an equal and opposite force, how is this gonna work? Like, what is this going to do? This doesn't make really any sense at all. But that will be explained in a short while. But before that, we realize that contact force is over here, and we have our normal force and our force of friction. I'm posing this with our angle to the vertical, so we can realize many more things, as this angle is also the same, as everything is along one line in using the vertical angles theorem. So, since we know that the angle is the same, we can find tension in terms of normal force, contact force, or even friction. So, that's just a very simple application of it. But, what was I talking about earlier about how, in reality, this is okay? Because, now, let's move on to another example. Well, not really an example to solve like I do in my previous videos, but an example to show you how instead of just impeding motion and making Newton's third law look like it just stops all motion, friction is actually the reason that there's any motion at all. So, for this example, let's take the block, a horse, and the cart. So, let's draw the floor. We have our horse over here. I know, not a very good drawing. And never mind, that looks like a spring. We can't really do that. Let's just have our horse be over here. Well, or a human pulling the cart. That's also fine. So this cart will have wheels on the ground, and we are pulling it in this direction. Now, by all things, you might think, oh, Newton's law would make it go this way, and since every force has an equal and opposite reaction, that means that this force, it can't move, and that there's no motion. But let's examine these two things over here, these wheels, and what force they exhibit. Now, this force over here is horizontal, and that's vertical. But when we have friction, friction is against the direction of motion for now. Or is it? Because this has a downwards force over here, and this has a downwards force over here. But by contact force, we realize that when we're moving this way, and when friction is, in fact, like that, we have technically our kind of force of friction over here. So that makes the contact force in this angle, and the force of this object 1 being contacted with the second object, object 2. Notice how I said the order. Object 1 is putting this force on object 2. So that means there's going to be a same force in the opposite direction. So we have the force of 2 on 1. So let's put this as C21. Now this goes in the same direction as motion and upward, but it's counteracted by the weight. So there's still no vertical momentum. But you realize there's still horizontal motion. And that's true, because when we have our force of friction and our contact force, the floor is not going to move. So, since we know that the floor is not going to move, that leaves a net force of this force to the right, and that's how friction, in fact, is the reason motion happens. Pretty surprising, huh? Who would have thought that the force that everyone teaches that's against motion actually works with motion and is the reason there's motion? So, there you go. That's an explanation of how friction makes motion possible. But I was going to do one more thing, and I am going to do one more thing. So, what we have over here is we have this formula for contact force. The contact force is equal to N times micro squared plus 1 root. So, how does that work? Well, we showed how it's by the Pythagorean theorem. But, as you can see, contact force times the sine of that angle theta is equal to micro n, or the force of friction, and contact force times cosine of theta is equal to the normal force. But what is theta exactly, and what is the coefficient of friction exactly? Now, as I explained in my last video, coefficient of friction is inherently a property that is shared between two surfaces depending on the type of molecules and the irregularities in the surface. Where I'm talking about irregularities, where we have these kind of particles sticking up and interacting with those other particles, thus creating what I was showing as friction. But let's go on a little detour. Let's see what this angle means. So, what we have over here is we have a normal force and a normal force. So, what if we divide the frictional force by the normal force? Then we'll get the coefficient of friction. So, the coefficient of friction is equal to the frictional force over the normal force. But that's just the opposite over the adjacent. And that's just the tangent of our angle. Now this is huge. This shows that the contact force depends on the surface also. As, let's write it as this. Theta is equal to tangent inverse of our coefficient of friction. And since this coefficient of friction directly depends on the surface, this will also directly depend on the surface. Thus, that means our contact force also is a property of the surface. So, what have we really proved and derived in this entire video? Well, I showed you what friction is. I showed you what contact force is. And I showed you how friction helps motion and how contact force and everything derived from it is really just another derivation from a property of the surfaces. So, I hope you found those realizations very interesting and unique, and I hope that you learned something new from this video, or even if you didn't, you just enjoyed watching it. So if you enjoyed watching it, please make sure to like, subscribe, and hit that notification button for more videos just like this. And make sure to comment down below any suggestions, tips, or anything you have for this channel, as it could really help me and this channel a lot, as I can make this better for all of you. So, learn some new physics, learn something new, enjoy life. Thank you so much. See you in the next one, and bye-bye.